Hi, hello, welcome back to NEET World. So, I welcome all of you for our IPE discussion, particularly here chemistry C60 by C60 session. Okay, so it means, so in these sessions we are covering IPE questions. I mean for class 12th as well as class 11th we are covering for both Telangana and AP students. For chemistry, maths, physics and biology, we are covering all the important questions to score out of marks. For example, in chemistry you have 60 marks, right? So these are the sessions helpful for scoring C60 out of 60. It means we have launched our C60 book here. So this book contains all the important questions along with their explanations. So using this C60 book from our NEET World YouTube channel, we will be explaining all these important questions. I hope you are following our sessions continuously on regular basis. See, in the last session I have covered all the important questions from electrochemistry. Whatever the important questions you required for your 8 marks, like scoring 8 marks in your class 12th IPE exam, I have covered in that session. ఓకే, మీరు లాస్ట్ సెషన్స్ కనుక చూసినట్టయితే నేను 8 మార్క్స్ క్వశ్చన్ ఫ్రమ్ ఎలక్ట్రోకెమిస్ట్రీ లైక్ వాట్ ఆర్ ద క్వశ్చన్స్ ఐ హ్యావ్ కవర్డ్, Kohlrausch law we have covered, and after that like galvanic cells like electrochemical cells are also covered. Then next what are fuel cells, that is also important question that is also covered. And then tarvata we have discussed Faraday's laws like electrolysis also covered. So these are the 3 questions covered from electrochemistry right now. So now in this session we will be discussing questions related to chemical kinetics for 8 marks first. Okay, once after finishing this, then we will discuss P block elements for 8 marks as well as organic chemistry for 8 marks. Then after we will be moving on to the 4 marks questions. I hope you are following these sessions. If not, if you are new to this channel, just click on the follow button and just look into our channel that whatever we discussed in the playlist, live playlist will be there now. So just go to the live, and in that you can just check all our chemistry, physics, biology discussions will be there for your IPE exams. Okay, yes. So in this session I will be explaining chemical kinetics right now. So here see, these are the full chapters, list of chapters we have. So in this book, if you wanted to access this book, yes, you can access this book through our app. So what is our app name here? So it is NEET World app. What is that? NEET World app. You can download it from Play Store, NEET World app, and you can access these notes. Okay, access these PDFs. Okay, and you can use it for studying, like your preparation purpose you can use this. Okay, right, let us move on to our discussion of these chemical kinetics, LAQs. Yes. Yes, this galvanic cell and fuel cells are discussed in the last class right now. So today we will be discussing chemical kinetics, particularly first question is related to collision theory. First question is related to collision theory. Let me check where exactly it is mentioned in the book. Here, yes, yeah. So look at these questions. Yeah, so look at this question. If you have seen this LAQ, first LAQ, first 8 marks question is from either electrochemistry or chemical kinetics right now. So further here I have covered Kohlrausch law from electrochemistry, and if not Kohlrausch law, you can expect a question from chemical kinetics, that is here, give a detailed account of collision theory of chemical theory of reaction rates of bimolecular gaseous reaction. So e question 8 marks ki we can have more and more chances, maximum chances are from either Kohlrausch law or from this collision theory. Okay, that will be the first question. Okay, so now look at here. what I am explaining here. So give a detailed account of collision theory of reaction rates for bimolecular gaseous reaction. Okay, it is very simple. See, I will explaining everything point to point from this material, and before doing this I will also be giving you the complete clarity on these points that I have mentioned here. See, look at this. So what they are saying, the collision theory was proposed by Arrhenius to explain rates of gaseous reactions based on the collisions between the reacting molecules. It means in order to happen a chemical reaction, for example ABR chemical reactants, these are undergoing reaction and to form some products. Now in order to make this chemical reaction to happen, so there should be collisions between these A molecules and these B molecules, then only the product then only reaction takes place and forms these products. Okay, so now what they are saying, see, according to this theory, the rate of reaction depends upon number of collisions per second and fraction of collisions possessing sufficient amount of energy to form products. It means, first of all, in order to happen a chemical reaction, in order to take a chemical reaction, collisions between the reactant molecules are must. What I am saying, collisions between the reactant molecules are must. Okay, so now all the collisions taking place between the gaseous molecules will not lead to the product formation. Only few collisions are responsible for that product formation. So what are the, like whatever the collisions that are responsible for product formation are there now, those are called fruitful collisions. What I am saying, effective collisions are fruitful collisions. Just look at here, the molecular collisions are necessary. See, the reacting molecules must collide with each other for any reaction to take place right now. So when the collisions are happening, then only reaction initiate, and that might be results to product formation right now. Right. So anyone in the chat box can interact. Let me check once. Yes, yeah. Look at here. So now what is the first criteria? Molecular collisions are necessary, that are must, and after that not all collisions are effective. See, between these molecules, it means if you are taking this as a container, in this chemical reaction is taking place. So in this container what we have, reactant molecules A and B are present. So between these two molecules there must be collisions. Now all the collisions that are taking place between this gaseous A and B molecules in the container will not lead to product formation. Only few collisions, out of that all collisions, only few collisions will lead to form product. Why only few? Because all of them are not effective, only few of them are effective. So those effective collisions are leading to product formation. Okay, that's why we are calling them as fruitful collisions. What we are calling? Fruitful collisions. Effective collisions are fruitful collisions. These points only you need to write in the exam. Then next, see one more point here, threshold energy. What do we mean by threshold energy? See, every reaction require a minimum amount of energy for the reactant molecules to convert into products. So the minimum amount of energy, see, for example this is what energy coordinate I am saying, this is what potential energy, here it is like this, and this is how the reaction is taking place. Reaction progress I am writing here. So this is reaction progress. Now what happens, here we have initially reactants are there with this much energy, and here some product is forming. So this is lower energy than the reactant, let us say. Now in order to go from this reactant to this product, so these reactant molecules must possess some minimum energy. What I am saying, these reactant molecules must possess some minimum energy to convert from this reactant to this product side, then only this reaction is taking place. So the minimum amount of energy required by these reactant molecules to happen this reaction is called as threshold energy. What I am saying, threshold energy. See, every reaction requires a minimum energy for the reactant molecules to convert into product. So that minimum energy is called as threshold energy. What I am saying, threshold energy. See, reactant molecules are having this much energy right now. Okay, so now still this much total amount of energy is required to attain this threshold energy. See, from here to here this gap is there, this energy gap is called threshold energy. What I am saying? Threshold energy. And but reactant molecules are having only this much amount of energy. Still this much amount of extra energy is required. The extra amount of energy required to attain this threshold energy, we can call it as activation energy. What I am saying? Activation energy. Now you have seen three new words here. One is energy of reactant molecules, energy of reactant molecule, one more is threshold energy, one more is activation energy. Actually I am repeating same thing in Telugu now. See ikkada manaki three things kavalama. So first one, ikkada reactant molecules ki inta energy undi kada. So ee reactant product laga convert kavadaniki, so it requires some energy, that is that energy, the minimum energy is called as threshold energy. But all the reactant molecules in normal states have energy lower than that threshold energy only. All the time ఏమంటున్నా ఈ రియాక్టెంట్ మాలిక్యూల్స్ కి జనరల్ గా కెమికల్ రియాక్షన్ జరిగేటప్పుడు ఈ థ్రెషోల్డ్ ఎనర్జీ కన్నా కూడా తక్కువ ఎనర్జీయే ఉంటుంది. ఓకే, అంటే ఆ కెమికల్ రియాక్షన్ అసలు జరగదు. సో అప్పుడు మనం ఏం చేయాలి? ఎక్స్ట్రా ఎనర్జీ బయట నుంచి సప్లై చేయాలి కదా. సో బయట నుండి ఎంత అమౌంట్ ఆఫ్ ఎనర్జీ సప్లై చేస్తున్నాం ఈ థ్రెషోల్డ్ ఎనర్జీని అందుకోవడానికి, దాన్నే మనం యాక్టివేషన్ ఎనర్జీ అని అంటాం. ఓకే, ద ఎక్స్ట్రా అమౌంట్ ఆఫ్ ఎనర్జీ దట్ ఆర్ సప్లైడ్ టు దిస్ రియాక్టెంట్ మాలిక్యూల్ to attain this threshold energy is called as activation energy. What is that? Activation energy. Okay, so now look at this, what I am saying. See, every molecule, the average energy of molecules at standard state and pressure is much lesser than the threshold energy. Yes, so this is our threshold energy, but reactants are having only this much, which is very much lesser. So that the difference between the threshold energy and average energy of reactant molecules is called activation energy. Okay, so it means threshold energy, threshold energy if I write, threshold energy if I write, this is nothing but energy of reactant molecules plus energy, activational energy. Now nothing but here activation energy is nothing but threshold energy minus energy of reactants. That's it. This is what the equation mentioned in this book. Okay, that's it. Everything is clear now here, whatever we are discussing? Yes, if the discussion is clear, just click on the like button. Yes, next thing here is now the activated molecules. What do we mean by activated molecules? Now these reactant molecules, after taking this activation energy, they get their energy, total energy equals to this much. This is threshold energy. Now whatever the molecules having this much amount of energy are called as activated molecules. What I am saying? Activated molecules. Now look at this, activated molecules that possess energy equal or greater than activation energy are called activated molecules. So these are formed in small number when normal molecules collide with sufficient energy. Okay, if normal molecules are colliding, see, if normal molecules are colliding, for example here AB, if a reaction is taking place between AA molecules, so it might form like one activated molecule and one normal molecule is formed. Now this normal molecule won't show reaction here, that will again collide with some other to get activated. Okay, so whatever the activated molecules are formed like this A star molecules are there now, so the reaction is taking place between this A star molecules only and finally leads to some product. Okay, so normal molecules collide with each other and some of them are get activated by that effective collision. Whatever the activated molecules are there, then the collisions between these activated molecules takes place to form final product. If there is any unactivated molecule, again that will collide with some other thing and try to get activated, and the next further reaction takes place to form product. That's it. This is what you need to understand. Okay, so that is what the indication mentioned here. Okay, right. Now how many collisions are taking place per unit time? That is given by collision frequency Z. So Z indicates collision frequency. Okay, so this indicates, this is nothing but number of binary collisions, that is Z here. The number of binary collisions per unit time, that is Z, is given as Avogadro number Na into sigma. It is here, it is collision diameter sigma AB, that is collisions between two molecules, AB molecules, that is collision diameter multiplied with here 8 kT. This formula you need to write as it is, kT pi by mu. Okay, so mu represents reduced mass and k represents here Boltzmann constant and temperature T. Okay, then next number of A molecules and number of B molecules, that's it, Na, Nb. So concentration of A and concentration of B, that is small a, small b, that is, this is what the indication you need to represent during the exam. Okay, right. Next thing is, so up to here you are clear with this right now. So the next thing is rate constant expression. So rate constant expression means how much faster a reaction is taking place, that is given with respect to K. So only a fraction of molecules, fraction of total collisions have energy greater than equals to kinetic energy, then hence rate constant K is given. See what is the rate constant indication here? See rate constant says greater the rate constant, greater is the reaction forward taking place. It means more is the rate if rate constant value is greater, because rate is equals to K into concentration of reactants, like this we are saying now. If rate constant value is greater, so rate also greater right now. So greater the rate constant, greater is the rate. Okay, so it means the rate constant here is indicated with three factors. One is P steric factor we can say, then next Z, and the next e to the power minus Ea by RT. So these are the three terms to be used here. So what do we mean by P? Probability factor or steric factor you can say, and Z means collision frequency is nothing but this one, whatever the formula you have written here, that is Z, and multiplied with exponential e to the power minus Ea by RT. So this minus Ea by RT, e to the power minus Ea by RT indicates fraction of molecules having energy that is sufficient for the reaction. Okay, that is sufficient for the reaction to happen. Okay, so this is indicates fraction of molecules having energy that is sufficient for the reaction. Now remember, collision frequency depends on this sufficient energy should be there, and they should have proper collisions, no? So for proper collision, proper orientation should also be there. So you need to look for the proper orientation also here. That's why we have P, that is a steric factor here, and the next is Z, and e to the power minus Ea by RT. These are the three factors giving our rate constant K. Okay, so that's it. You need to indicate this one in the exam, as well as this frequency Z. What is the formula you need to indicate? That's it. Okay, right. Okay, so now there are something called energy profiles. What do we mean by energy profiles? Energy profiles indicates whether a reaction is endothermic or exothermic. It means, I will tell you, it is very easy. See, during a reaction, for example, a reaction is taking place from A to B. Some products is forming from reactant A. So now this is the energy of reactant. Energy of reactant I am indicating here, and product energy somewhere here. So which is having greater energy here? See, this is the this is potential energy now. So it is increases as we move upside. So this is at here only. So which is close to this 0. It means energy of reactant is lesser when I compare with the energy of this product. Okay, energy of reactants are less when compared with the energy of product. Okay, so now we will be having some minimum energy to happen this reaction, that is called threshold energy. This is the limit, energy barrier. Okay, so reactant molecule to achieve this energy barrier, after crossing that only these products are formed. Okay, so now what you are seeing here, see, during the reaction energy of reactants are this much, and the next this is the energy of products. So now if you take the difference of product and reactant energies, like energy of products minus energy of reactant, which is greater? Here energy of product is greater now, so larger value minus smaller value. So it means the enthalpy change during this reaction, some amount of heat is like absorbed, that's why energy of product is greater. It means this is positive now. See, bigger value minus smaller value. For example, if it is 100, energy of product is 100, some energy of reactant might be some 60, 70 only. So that you are getting plus 40 now. So plus 40 means this much amount of energy is absorbed during the chemical reaction. So whenever you have this kind of profile, you are getting enthalpy change, energy change or heat change during the reaction as positive number now. So it means this whatever the positive number you are getting, that amount of energy is absorbed during the reaction. So you should call these reactions as endothermic reactions. What is that? Endothermic reactions. Okay, so this is energy profile diagram for endothermic reaction. So which energy is greater? Energy of product is greater than energy of reactant. Okay, so this is what you need to remember, and during this reaction, during this endothermic reaction, energy is absorbed from the surrounding. What happens? Energy is absorbed from the surrounding. So now look at here. So this is an extra point I just want to add, so that you can also able to solve questions related to EAP set if I add this point. So just look at here, try to understand what I am saying. See, this is the energy. See, this is the energy. So from here to here, whatever the energy gap is there now, so this gap represents energy of reactants. What it indicates? Energy of reactants. And this gap is represents energy of products. What I am saying, this represents energy of products. Now the energy difference between the product energy versus minus reactant energy will be enthalpy change. How much amount of energy is released or absorbed given by this difference. Okay, it means energy of products minus energy of reactant. And see, the energy difference from like this point to this point, this term like this top point, this is called the threshold energy. I am saying E threshold energy. ETR means E threshold energy. Now our reactant molecules are having only this much energy, but in order to make this reaction, they should achieve this point now. It means still this much amount of energy is still required. So for making this forward reaction, how much energy is required from here to here? It means whatever the extra energy is required, that is called activation energy for forward reaction. See, this is forward reaction A to B. So this is A forward. Okay. Now if you want convert from product to reactant, so it means this is the activation energy you need to consider. This is EA for backward reaction, EAB, and this is EAF I am writing. Hope whatever we discussed till now are very clear without having any confusions. Right now, if this is clear, just tell me clear sir in the chat box or click on the like button, so that I can confirm that you are following the session very effectively. Yes. Next thing here is exothermic reaction graph you need to understand. See, this is very simple. Again, exothermic means what? So in these reactions, in exothermic reactions, energy is released out from the system. If in this system, it means in this beaker some reaction is taking place. For endothermic, it will be absorbed, heating, heat is absorbed from the outside. But if I say exothermic, heat will be comes out of this system. It means the reaction should be indicated in this way. So this is called a reaction coordinate. This is reaction coordinate or reaction progress. So it means how reaction is taking place as time goes on, and this is potential energy of that reaction. Okay. So if I say this is the energy of reactant molecules, reactants are converting into product. If I say this is the energy of reactants, okay, and if I say this is the energy of product, now the difference between them, see, this is a threshold energy, like this we have. Okay. So now this is the energy, activation energy for forward, EA for forward, this is EB for backward, EA for backward. Okay. So now the difference between these two, if you observe this difference, what is the difference? Here you have enthalpy change. You can write delta H will be equals to energy of product, final energy minus initial energy, energy of product minus energy of reactant. See, energy of product is lesser compared with the energy of reactant right now. So this one is lesser, this one is greater. So small minus bigger. So it means it is a negative value we will get now. Something like energy of product is here something like 30 and energy of reactant is might be some 50. So it is 30 minus 50, it means minus 20 you are getting now. So this is what the enthalpy change. It means this much 20 joules of energy might be released during a chemical reaction. Like that, some amount of energy is released from the system during that reaction. So that is called exothermic reaction. So this is the indication of that exothermic reaction. Okay, so you need to indicate this kind of graphs for this particular question. Okay, if they ask in the exam. Okay, so is this clear or not? Yes, I hope this is clear, whatever we are discussing till now. Whatever we have discussed till now is clear. Right, right. And then next here I just want to explain one more question. See this Kohlrausch law, if you haven't seen this video on Kohlrausch law, just watch the first session of this one class 12th IPE discussion. Definitely you can you can answer this question if it comes in the final exam after watching that video. Okay, right. Now the next discussion is on the difference between molecularity of a reaction and order of a reaction. It means they will ask like this: what is molecularity? What is molecularity of a reaction and how it is different from order of a reaction? So what is molecularity and order here? See, molecularity is a theoretical one, okay, that comes theoretically, but order comes from experimental determination. See, look at here, the number of atoms, molecularity means the number of atoms or ions or molecules participating in the rate determining step. Okay, so now if you have studied about SN1 reaction, SN2 reaction, like that, so during the reaction we are using a term rate determining step, RDS step, like that we are saying now. So in that rate determining step, how many molecules, how many reactant molecules are participating, that gives our molecularity of that reaction. The number of atoms, it can be atoms, ions or molecules that are participating in rate determining step, that is slowest step of that chemical reaction, is called molecularity of that reaction. Okay, so now it indicates how many reacting species colliding simultaneously to bring about that chemical reaction. So number of reactant molecules colliding during that chemical reaction comes from this molecularity. Okay, right. Now if only one molecule is involved in the collision, if one molecule only involved, you can say this is a unimolecular reaction. Okay, so what is that? Unimolecular reaction. If two molecules are involved in that collision, then you can say in that rate determining step, you can say it is a bimolecular. If three molecules are involving, trimolecular, like that, depending upon number of molecules, reactant molecules or ions involving in the rate determining step, we can say whether it is unimolecular, bimolecular, trimolecular, like that. Okay, right. Next, differences between order and molecularity. So what is the difference between order and molecularity? See, order is nothing but it is a sum of powers of concentration terms appearing in the experimentally determined rate equation. For example, here I am saying a reaction is there, like A plus B giving rise to some product. A plus B giving rise to some product. I am saying the order with respect to A is 1, order with respect to A is 1, then order with respect to B is 2. So this order means these values comes from, this 1 and 2 values comes from experimental only, not theoretically. Okay, for complex reaction these values comes from experimental only. And there is one more type of reaction like elementary reaction, complex reactions. If in the exam if they mention it is an elementary reaction, it means whatever the coefficients are there here, those will be their orders. Those will be the order. See, if I mention it as 1 here, so the order with respect to reactant A will be 1 and order with respect to B also here 1 mentioned means 1. If it is mentioned as 2, then order with respect to B will be 2 and order with respect to A is 1. Just look at their coefficients, those will be their orders for an elementary reaction. If it is a complex reaction, what I am saying, if it is a complex reaction, we cannot take these coefficients as their orders all the time. It may or may not be equal. Okay, so that's why order for a complex reaction comes from experimental data only, not theoretically. Okay, so in the exams we need to do any experiment? No, they will mention whether this is first order, second order with respect to A, with respect to B, they will mention, then you can get that idea. Okay, anyways they won't ask that kind of questions here, just you need to differentiate what is mean by order of reaction, molecularity of reaction, that's it. Okay, so order means it is a sum of powers of concentration terms appearing in the experimentally determined rate equation. If this is the equation involving in the rate determining step, okay, or if I say this is a primary, I mean elementary step, here having 1 and 2, then order should be written like this: rate is equals to K concentration of A reactant, whatever reactant we have, I am writing that A, and if I say order with respect to A is 1, you should write A to the power 1, and if I say order with respect to B, then it should be 2, because this 1, 2 values are the individual orders for A and B. Again that values comes only from experiment, not theoretically. Okay, for only elementary reactions, if it is mentioned like this, take their stoichiometric coefficients as their orders, that's it, not for complex reactions. Remember this statement. Okay, and the next here look at this, see, order of reaction can be 0, order of a reaction can be 0, or it can be fraction, or even it can be negative value also. Order of a reaction anedi 0 ayi undochu, positive numbers like 1, 2, 3, 4 ayi undochu, or it can be negative values also, -1, like that also it can be. Okay, but most of the cases it will be positive, like 1, 2, like that only. Okay, right. Next one, order is determined experimentally by studying how the rate depends on concentration. Okay, so how the rate is changing with respect to concentration of reactant AB during the reaction, this order will be determined, that is what experimentally determined. So order refers to the overall reaction, so order may change with temperature and pressure, so order may change with temperature and pressure, so order may be fractional or it can be also 0. Now just compare with molecularity. Molecularity is the number of molecules or atoms that are taking part in the rate determining step. So number of molecules that are involving, reactant molecules that are involving in the rate determining step is considered as its molecularity of that reaction. Okay, and the next one here is molecularity of a reaction is always a whole number. Okay, it will be always a positive value, like it can be 1, 2, 3, 4 like that, but it cannot be a 0 and it cannot be negative also. Why it cannot be 0 or negative? See, molecularity is nothing but number of molecules colliding in the rate determining step. Now, if there is no molecule colliding in the rate determining step, see, if no collision, no reaction initiation. No? So, if no reaction is taking place means no molecules colliding means there is no reaction only taking place, therefore no product formation. That's why if molecularity is 0, it cannot be possible. So, always molecularity will be a whole number, like positive integer here 1, 2, 3 like that only. Okay, right. Next, molecularity is determined theoretically from the mechanism of reaction. So, what I am saying, during the mechanism, how many reactant molecules are participating in the product formation. Okay, like how many collisions, how many effective collisions are participating, happening in that, how many molecules, reactant molecules are participating in that collisions during the rate determining step is considered as its order, its molecularity. Okay, so molecularity is determined theoretically from the mechanism of the reaction. So molecularity refers to the slowest rate determining steps, to the slowest step, that is rate determining step of the mechanism. For example, in SN1 reaction, you are saying the SN1 reaction, why we are saying SN1? So 1 represent, it is unimolecular reaction. What I am saying, it is a first order unimolecular reaction. It means we have involvement of carbocation right now. So formation of that carbocation as intermediate. So only reactant molecule, that substrate is involving here. So the molecularity will be 1 for that. Okay. So now molecularity does not change with temperature and pressure. It will not change with temperature and pressure, whereas order changes. Now molecularity can never be 0 or fractional, but order can be 0, fractional or negative also. But here molecularity cannot be 0 or fractional, because half molecule will not participate in the collisions. It can be either full, like one molecule, two molecules only, it cannot be like negative molecules or half or like fractional molecules like that. Okay, it cannot be zero also, it always a positive integer. Okay, remember this number. Okay, so these are the differences between molecularity and order of a reaction. Okay, and the next here we have few more things to discuss. So these are some examples. Bimolecular gaseous reaction is mentioned here. So what is this bimolecular gaseous reaction means? See here, bimolecular. So in this reaction bimolecular, it means two molecules are involving here. So AB or two molecules are involving in the rate determining step. Then we can say molecularity is 2, A and B. So two molecules, so we can say bimolecular reaction. So now here example, so 2HI, here two molecules of hydrogen iodide react simultaneously, hence the reaction is called bimolecular. Like this you need to give one example also during your exam. Okay, in the exam you need to mention some examples. Next, trimolecular gaseous reaction, it means three molecules, reactant molecules are involving in the rate determining step and forming some product. So example here is two molecules of nitric oxide and one oxygen molecule and forming 2 NO2. It means how many molecules are involving here? Here 3. So 3 molecules, 2 NO and 1 O2 participate in the slow step, hence the reaction is called trimolecular reaction. Okay, so that's it. This is about order and molecularity of reaction. See, you need to define what is molecularity and the next what is order. Next, write the comparison points. After writing comparison points, then show some examples for order of a reaction and molecularity of a reaction, like this kind of examples for molecularity of a reaction. That's it. So that you will get full marks based on the marking scheme. They will give you good marks as per your presentation in the exam right now. So now here we have one more question. Describe the salient features of collision theory of reaction rates of bimolecular reaction. Again we have studied this kind of question already, but there is small variation here. Just go through these points because almost same it is. So I do not want to waste the time on again same discussion. So just go through these points because already we have discussed collision theory, again collision theory only here. So everything is same, that but they mentioned little difference in the question. So that's why I am saying you to go through the question so that you will get complete clarity on this model question also. Okay, right. Next, electrolysis and give Faraday's first law of electrolysis and second law of electrolysis we discussed in the previous class. I mean in the yesterday's discussion we are completed this discussion, this question discussion is over right now. The next here we have again look at this order of the reaction based question again. I mean this is an extra question you need to know. So what they are saying here, just look into it, or define order of the reaction and illustrate your answer with an example. Define molecularity of reaction, illustrate with an example. Same, there we have studied about difference, here they are giving about difference, I mean or defining them. So just look at this, what do we mean by order of reaction? Order of a reaction is defined as sum of powers of concentration terms in the rate equation. It means whatever the reactants are involving, like A, B are reactants forming some products. Now you need to write order of a reaction is equals to like order of a reaction comes like this, like you can write rate equation as involving A, reactant A and a reactant B. Now whatever the powers you are writing to this reactant A and B are considered as orders with respect to this A and respect to B, and total order if they ask you should write it as M plus N will be gives you total order of that reaction, total order of the reaction. Okay, so now this M and N values how do we get? We just now discussed, it is an experimental value. Order of reaction determined experimentally. This total order, individual orders comes from experimental data only. So it can be positive, negative, 0 or fractional value. Okay. Okay. So now you can get this order of reaction. See, you can get this order of reaction from some different method. That is what integrated equation method, integrated equation method. Okay, or you can say trial and error method. And the next one is half-life method. What I am saying? Half-life method. So what do we mean by half-life? How this T half, it means for a chemical reaction. For example, I am writing for a first order reaction, K is equals to given by x by T. So how this x by T, all these are integral equations. From this, if I want T half, so I want T, I can say T is equals to x by K. Okay. So now x is the indication for concentration. Concentration is nothing but the time required to half of the completion of reaction. It means concentration of reaction reactant should become half completed. Okay. It means if A is a concentration, now it becomes A by 2. Okay. Then next K naught. So here you got A by T half is equals to A by 2 K naught. That is T half is directly proportional to A in case of 0 order reaction. This is in case of 0 order reaction. Now for first order, it will be independent. For second order, T half will be like this, 1 by A to the power 1. So it means T half is inversely proportional to A. So for second order, I am saying A to the power 1. For third order, it is A to the power 2. So he is generalizing this as T half is inversely proportional to 1 by A to the power n minus 1. What I am saying? 1 by A to the power n minus 1. So if you put n value 0, what happens? T half is inversely proportional to 1 by A to the power minus 1. A to the power minus 1 is nothing but, in the numerator you can write it as A now. So that is nothing but this kind of relation you will get, this kind of relation you will get for a 0 order reaction. For a first order reaction, T half is equals to 1 by n value is 1, because I am saying first order, 1 minus 1 0. So this is something power 0 will be 1 now. So T half is independent of this initial concentration you will get. For second order, so n value is 2, T half will be inversely proportional to A power 1, that is A 1 by A you will get. Like that, they have given this half-life method for finding order of the reaction. By looking at these half-life values, we can find this n value. So this n gives us order of the reaction, that's it. Okay. And the next methods are here, Van Hoff's differential method, Ostwald's isolation methods. These are some other methods to calculate orders of the reaction. Okay. The next. So when it comes to molecularity, molecularity is nothing but it is a number of atoms, molecules, ions that are participating in slowest step, that is rate determining step is considered as molecularity of reaction. Okay, right. Right. Next one is, this is one more question you can expect, that is dependence of temperature on rate, like dependence of rate of a reaction on temperature, or in the other way they will give, discuss the effect of temperature on rate of a reaction, derive the necessary equation in this context. So this is a less expected question, but yes, you need to be aware, because by chance if they are making a question paper completely of different pattern, yes, you need to be aware. Okay, that's why I am adding this question also. Mostly we can directly say that most of the cases question is from Kohlrausch law or from collision theory. These are the only two questions which comes as a first question as your LAQ. Okay. Okay, if not these, you can have a galvanic cell and fuel cell as a second question. Okay, as a alternate question for this. Okay, right. Look at this. What they are saying, discuss the effect of temperature on rate of a reaction, discuss necessary equation to derive necessary equation on this contest. Okay. See what they are saying, the effect of temperature on rate of a reaction. Generally, I will tell you one oral discussion first, then we will go through this. See, generally when temperature increases, rate of reaction also increases. What I am saying, if temperature of a reaction increases, rate of a reaction also increases. It means మనం temperature increase చేస్తే ఆ రియాక్షన్ యొక్క ఫాస్ట్నెస్ అనేది కూడా, రియాక్షన్ యొక్క స్పీడ్ కూడా పెరుగుతుంది. రేట్ ఆఫ్ దట్ రియాక్షన్ ఆల్సో ఇంక్రీజెస్. ఓకే, సో మరి ఇది ఎలా ఇంటర్లింక్ చేస్తాం అని అంటే, సో దీన్ని ఎక్స్ప్లెయిన్ చేయడానికి మనకి అర్హీనియస్ ఈక్వేషన్ అనేది ఒకటి ఉంటుంది. సో అర్హీనియస్ ఈక్వేషన్ గివ్స్ డిపెండెన్సీ ఆఫ్ రేట్ ఆన్ దిస్ టెంపరేచర్. రైట్ నా, dependency of temperature, dependency of rate on temperature. Okay, so that is one equation, that is what I am going to explain. And before going to this, we have one more experimental observation, that is observed. See, ee temperature eppudaina kuda oka 10 degrees increase chesarankondi, rate increases 2 times. See what I am saying here, if temperature increased by 10 degrees Celsius or 10 Kelvin, then rate becomes 2 times. It means at T1 temperature, if I am saying rate of reaction is R1. Okay, now I am increasing this temperature from T1 to T1 plus 10 degrees, extra 10 degrees Celsius is increased. Now the rate here R2 becomes 2 times of R1, 2 times of R1, or sometimes it becomes 3 times of R1. ఓకే, సో ఇప్పుడు మనకి ఇందులో ఏం అర్థం కావాలి, ఇన్ జనరల్ ఫర్ ఎవ్రీ 10 degrees రైజ్ ఇన్ temperature, the specific reaction rate becomes nearly twice or even thrice of its original value. It means for every 10 degrees rise in temperature, rate is increasing by 2 times or sometimes 3 times. That's it. ఓకే, సో ఇక్కడ మనం 2 times 3 times అంటున్నాం కదా, దాన్నే టెంపరేచర్ కోఫిషియంట్ అంటాం. ఏమంటాం, temperature coefficient. We can call it as temperature coefficient. Okay, so now look at here, see this temperature coefficient mu is equals to, how can you give, this is nothing but a ratio between K 10 degrees Celsius, like temperature at T degrees Celsius, in the numerator temperature at T plus 10 degrees Celsius, that value becomes how much, 2 times or 3 times. Okay, so now you can write this as K T plus 10. So T indicates some T degrees Celsius, like for example T30, it means rate constant K 30, rate constant at 30 degrees Celsius, and K 40, that is rate constant at 40 degrees Celsius. If I say T as T degrees, this will becomes what, T plus 10 now, that is what the taken here as a ratio. Okay, so the ratio of rate constant at T degrees Celsius and upon here what we have K, it means rate constant at T plus 10 degrees Celsius is observed to be 2 times or 3 times. Okay, it means rate R2 is equals to something like either 2 or 3 to the multiplied with R1, that is nothing but here I am saying a new term called temperature coefficient mu. Okay, this mu, how it will be coming, based upon temperature difference. If I say only 10 degrees Celsius, then it will be simply 2 times, you can write here 2 to the power 1. Okay, but if sometimes I am saying temperature rising from 10 degrees to like 30 degrees I have mentioned, now it is converting into 60 degrees. Now what is the temperature degree, temperature difference, this is 30 now, so 60 minus 30, 30 now, so it means how many tens are there, some 30 to 40, 110, next 40 to 50, one more 10, and from here to here one more 10. So it should becomes how many times, it should be, if here it is R1, this should become 2R1, and here it should become 4R1, and here it should become 8R1, like that. This is the final. So that's why the final rate is equals to R2 is equals to mu to the power delta T by 10 I am writing. So what is this delta T, indicates temperature difference. Okay, so mu, if I say rate is increasing 2 times for every 10 degrees, 2 power 30 by 10 into R1 gives your R2. So this is nothing but 2 power 3 R1, that is 8 R1. Yes, see here also we got 8 R1. So this is what you need to understand from the discussion. Okay, so this is says about effect of temperature on rate determining step. Okay, this says about effect of temperature on rate determining step. Okay, so now one more equation, what I am saying, Arrhenius established an equation, relation between rate of a reaction, that is rate constant with a temperature. Okay, K is equals to A e to the power minus EA by RT. Okay, so if temperature increases, rate constant also increases. Okay, that's it. Okay, next. So if you apply log on to this, what happens to this? See, here A is called Arrhenius parameter, where K is rate constant, EA is called as activation energy, and T is temperature. Okay, so now if you send this A this side, what happens? K by EA, which is equals to e to the power minus EA by RT. Okay, like this you can write. Now send this E to this side, this becomes exponent, like exponent, E becomes ln now. So you can write ln of A by K, just inversing this so that it becomes positive value now. EA by RT plus EA by RT it becomes, like this you can write right now. Or if you want to write as it is, like ln of K by A is equals to minus EA by RT, like this also you can write. Now from this I want only K, I am sending this A that side, so ln K becomes equals to minus EA by R into 1 by T. Log A by B means what we are writing, log A minus log B now. So that log B I am sending that side, it means this is minus ln A becomes plus ln A here, like this you can write. Okay, so now how do you got this equation? If you observe, this is something like y is equals to mx plus c type graph, y is equals to mx plus c type graph. Okay, so means you can draw a graph here, so you can draw a graph here like this. What is our y here? ln K, and what is our x here? 1 by T. Okay, so now slope is in negative terms now, slope is in negative terms, so slope should be negative, intercept should be positive, like this you should indicate. What is our slope there? Minus EA by RT, R minus EA by R. What about ln A here? ln A is like intercept is ln A, that's it, like this you need to indicate. So if you indicate in this format, like representing the equation along with this graph, definitely you can get full marks. Okay, yes. Next we will discuss further. Is this clear? If this is clear, just mention clear in the chat box. Yes. Next, next we will discuss few more things. This graph, everything is discussed, and you know, if there is two temperatures, two different temperatures, till now we have discussed at one particular temperature. Now if I am giving at a temperature T1 and T2, it means if temperature changes, rate constant, that K also changes, like you are writing now. So log K is equals to minus EA by 2.303 or 1 by T plus log A we are writing right now. This is what the equation we are writing. This is what the equation you are writing. Okay, so in this equation, if I mention temperature is T1, then rate constant becomes K1. If temperature T1, rate constant K1. If temperature T2, rate constant will be K2. Like this you need to take. Okay, so from these we need to write an equation, like take this K1 K2 here, therefore you will get from that log K2 by K1, it means like log K2 by K1 will be equals to EA by 2.303 or 1 by at T1 temperature we are writing K1 like that, 1 by T1 minus 1 by T2. Okay, so this is the final equation we can say. So at temperature T1 you have K1, rate constant K1. At temperature T2 you have rate constant K2. You know guys, this equation you are learning it for IPE, right? Same equation is very useful for your JEE and EAP set exams also, because they will mention this K1, K2 values and T1, T2 values. They will ask us to calculate activation energy. Okay, like this also we can expect the questions. Okay, right. So I hope the discussion whatever we have did here is completely clear without having any confusions right now. So now one more point here I wanted to add here for this discussion is one more question I have. Just we will finish with this so that chemical kinetics is also done. Okay. Now they will ask about catalyst. See, discuss the effect of catalyst on kinetics of a chemical reaction with a suitable diagram. See, it is very simple. It is very simple. There are two types of catalyst. First of all, what do we mean by catalyst? It will alter the rate of a reaction. Okay. So it means it will make the faster the rate of reaction, or it can also have ability to slower the rate of reaction right now. So those catalysts which are increasing the rate of reaction, which are faster the rate of reactions, are called as positive catalyst, and if it is slowing down the reaction, then we can say it is a negative catalyst. Okay. So now catalyst is a substance that enhances the rate of a reaction. It means reaction yokka speed ni penchutundi, danne manam catalyst ani antam. So ikkada chudandi, a catalyst is a substance that enhances the rate of a reaction. Okay. So got it now what I am saying? You need to check that whether a given catalyst is positive or negative. See, a positive catalyst enhances the rate of reaction. Okay. So now once again read, a catalyst is a substance that enhances the rate of reaction without itself undergoing any chemical change. It means catalyst cannot participate in the reaction, but it will alter the rate of reaction. It will not involve in the chemical reaction. It means it will not undergo any changes. Okay, but it will alters. It means it will make the reaction to happen faster. Okay, so it means, for example, here manganese dioxide Mn2O2, MnO2, speed of the decomposition of potassium chlorate. See, potassium chlorate is there now. So this potassium chlorate undergoes decomposition. So this decomposition reaction is increased, like fastered, like altered. It means enhanced, rate is enhanced with the help of manganese dioxide MnO2. The presence of MnO2 makes the reaction to proceed much faster. Okay, that makes the reaction to happen much faster. Okay, then next, how catalyst works? How a catalyst works? A catalyst speed of a reaction by offering an alternate reaction path or a new mechanism with a lower activation energy. It means just now we have studied about activation energies, everything by drawing their graphs right now. So here I am writing potential energy, and here I am writing reaction coordinate, means reaction progress, like this we are writing. So for example, a reaction is taking place in which it is having activation energy on like energies like this. Okay, this is the threshold energy and this much amount of activation energy is required. So now this is in absence, let us say this is in absence of catalyst. If I say, now what happens in presence of catalyst? Now it will be altering a new path, it will be giving a new path. See, it reduces energy barriers between the reactant and product. So this is what threshold energy we are saying, or energy barrier we are saying now. So now that barrier will come here. Okay, and see here I am writing with this color. See, now you are going to get a new pathway. See, this is new pathway now. So previously you required this much amount of energy to activate, to get activate, this much amount of energy is required, but now you only require this much amount of energy. It means you are requiring lesser amount of energy now. So this is in the presence of, this is in presence of catalyst, this is in absence of catalyst. Okay, so if lower energy is required for this getting activated, So it means more number of molecules will get activated and the reaction will proceed faster when we compare with the absence of catalyst. That's it. This is what you need to understand here. Okay, right. Now look at this. Lower the activation energy means more molecules have sufficient energy to react. As a result, the reaction proceeds with a faster rate. Okay, so catalyst does not alter Gibbs free energy or enthalpy change during the reaction. See, whatever the difference we have here, that will remains constant, but only this energy barrier previously at the top now is coming to the lower state. That's it. So energy barrier coming down, that is what the only difference we are seeing. There is no enthalpy change difference here. Enthalpy change delta H will be remains same in absence of catalyst and in presence of catalyst, because these energies are not altered, only this energy barrier is getting down, reduced here. That's it. Okay, so it only affects on the speed of a reaction. Okay, it means it will faster the reaction or slower the reaction. In presence of positive catalyst, it will be faster the reaction. In presence of negative catalyst, it will slower the reaction by giving a newer path which is having greater activation energy, greater energy barrier. Okay, right. These are the two things. One is positive catalyst decreases the activation energy like energy barrier and make it to be faster reaction when we compare with the absence. Okay, that's it. Absence of catalyst. That's it. Okay, so catalyst accelerate the spontaneous reaction, but they cannot make a non-spontaneous reaction to happen. So it means catalyst does not like initiate the reaction, but it will faster that initiated reaction. It will not start a new chemical reaction, but it will increases the rate, it will increases the fastness, speed of that reaction. That initiated reaction is there now. So for that reaction, it will help by increasing the speed. That's it. But it will not initiate the reaction. Remember this. That's why it does not make a non-spontaneous reaction to happen, but it will increases, accelerates the spontaneous which is happening on its own. But if it is happening in its slow manner, this catalyst will make this reaction to happen with a faster speed. That's it. That is what accelerating the spontaneous reaction, but not make a chemical reaction that is non-spontaneous. Okay, right. These are the differences for spontaneous, non-spontaneous and effect of catalyst on those reaction. Okay, so this is the energy profile diagram that we have already written for this. Okay, and our next question is from second LAQ question is from P block elements right now. So P block elements, and or else the third question is from organic chemistry. So in the next session we are coming up with a discussion of these P block elements as well as organic chemistry LAQs. Okay, so just stay connected with our NEET World channel, and if you have any confusions or any doubts, feel free to mention in the chat box. So make your class notes from this and prepare well for your IPE exams. So thank you for watching. Stay connected with us. Thank you.